Hello everyone, welcome back. In the last class we discussed the least square reconstruction and also we started the green Gauss reconstruction, and what we saw that in the green Gauss reconstruction, if you want to get the value at the cell center, okay, which is I here, it can be calculated. So, this is let us say delta phi I, and if the cell volume cell has a volume of omega I, can be calculated sigma phi k n k delta s k by omega I, right. So, where k is the basically phase, this is my n k, and this distance is delta s k, right, and you have to basically integrate over all the phases, right. So, here we are using the value, the phi k is the value at the phase center, right. So, we stop that, how do we get the value phi k at the phase center? So, there are two ways to get the value at the phase center. One is just the cell based, right. So, what we do is that we have information about the neighboring cell. Okay. So, if I can just draw this line here. Okay. So, I want the value at k. Okay. Okay. So, if you have let us say I and j here, let us say this is my I and j. So, and we want the value at k, which is at the center here. So, you can just say that okay, the value at k, the phi k will be some weighted average of value at phi I and 1 minus f phi j, right, where this f is nothing but your distance of x I minus x j by x f or x k minus x j, right. So, you calculate the factor here from this to this, and you use the value with respect to I and j. Basically, depending on how far your cell centers are, okay, they will have you can use those weights to calculate the weighted average at k, right. So, if the cells are very far from the phase, it will have lesser weightage. If the cells are very close to the cell centers are very close to the phase, it will have higher weightage, right. So, you can easily calculate it, and this sounds very nice. Only problem here is that sometimes your cells can be very different. Okay. So, let us say that I have a cell like this, okay, and its neighbor is something like this. Okay. So, the first one has the cell center here, okay, and the second one has got the cell center somewhere here. Okay. And because you are assuming the linear interpolation, so what is happening that you are calculating the value somewhere here, right. But in the last class we discussed that you need to get the value at the center of the phase, which is here. Okay, this is my center of the phase, but when we are using the cell based weighted averaging to calculate the value at f, you are getting the value at f prime, right. So, it is quite far from the phase center, right. So, the approximation that you are taking, that my integral of basically phi k or just phi, okay, on the phase. So, phi is value on the phase, and then you have basically ds or d gamma, if you write here, is equal to phi k delta s k will not be valid, right. It is only valid when the k value is at the center of the phase, right. So, this gives you a skewness error, okay, and your calculation of gradient will not be correct. Okay. So, the other approach is that instead of using the cell based, you calculate the value based on the nodes, right. So, what will you do there that okay, remove all these parts here. Okay. Yeah. So, this phase has got two neighbors here. Okay. So, let us say this is my V1, V2 and V3. Okay. So, we can calculate the value at this phase center, okay, by taking an average of the values at the nodes, if we know the value at nodes, right, V1, V2, V3. So, let us say you want to calculate value here f, Okay, so this f will be 5 v2 plus 5 v3 by 2, right. Similarly, let us say this is my another phase, this is f2, phi f2 will be 5 v3 plus 5 v1 by 2, right. If you go to 3D, so each phase may have many vertices, right, depending on what kind of element you are using, what kind of polyhedral element you are using. So, let us say if you are using a pyramid, right. So, then it will have at least what is there on the vertical. So, this is a triangle, right. So, each of the face will have 3 vertices. So, you have to take the average of all 3. So, in general you can write basically phi sigma v by sigma of number of nodes, right. This is the value of sigma f, right. This is the value that you are getting the face center. So, in 3D, for example, if you have 3 vertices, okay. So, this is my face center f and it is got what is v1, v2, v3, right. So, then you will have take the average of all 3 values. If it is a quadrilateral face, okay. So, then you will have v1, v2, v3, v4 and you can take the average of all 4. In the case of 2D, okay, you have only 2 nodes at every edge, okay, or every face. So, you can just take the average of those 2. So, this is more accurate because you are doing node based calculation. So, if you know the value of nodes and if you have estimated it well enough, the average of that will always come at the center, right. So, this is more accurate, okay, but it requires values at the vertices, right. So, you need to get the value. Remember, in the cell based finite volume approach that we are following, we are storing the values at the cell center, okay. So, we are storing the values here, okay. This is my I, we are not storing the values at the vertices. So, somehow from this I we need to get the values at the vertices or nodes, okay. So, this is of course more expensive because from cell center to you calculate the value at the nodes and from nodes you calculate the value at the face center, right, but it is more accurate. The other thing is that you need to do more bookkeeping here, right, because you need to store the values at nodes also, okay. Earlier you could only use the store the value at the cell center and do away in your let us say either in least square or in the Green-Gauss cell based approach, but here you have to get the values at nodes also, right. So, how do you get the values of nodes? So, that is not very difficult, okay. So, you can use some kind of weighted average to get the values of nodes. Let us say this is my node V and these are the cells connected to this, okay, 1, 2, 3, 4, 5. So, all I need to do is that some kind of area average, okay. So, 5A will be basically AL phi L by AL, right. So, this AL can be your distance, right. So, it can be let us say this is my D1, okay. So, this will become D1. So, this will become D1 phi 1 D1 phi 1 plus D2 phi 2 plus D3 phi 3 plus D4 phi 4 plus D5 phi 5, okay, and by D1 plus D2 plus D3 plus D4 plus D5, okay. So, this makes sense that you have taken an area average. Why I am calling it area is because in 3D it will not be a distance, but it will be an area, okay. So, but sometimes you can have elements which is like something which is shown here, right, and if you are just taking an area average which is in this case distance. So, basically giving more weightage to the value which are farther from the node, right. So, if you use the same formula here D1, so D1 is very big, okay. D1 is very far from this cell center from the vertex, okay. So, this is your distance D1. So, D1 is very far. So, you are giving more weightage to D1 which should have gotten less weightage, right. Similarly, D2 also you are doing the same, right, and the weightage of 3, 4 and 5 are going down because they are multiplied by the smaller distance value, right. So, in these cases you can use the inverse area average, okay. So, where you can basically use this phi v will be basically 1 by D1 phi 1 plus 1 by d 2 phi 2 plus 1 by d 3 phi 3 plus 1 by d 4 phi 4 plus 1 by d 5 phi 5 and divided by 1 by d 1 plus 1 by d 2 plus 1 by d 3 and plus 1 by d 4 plus 1 by d 5. So, typically in your finite volume formulation, you will have many skewed elements, okay, or the elements with very high aspect ratios. Okay, let us say in the boundary layer, if you go to very close to the wall, for example, your elements could be like this kind of element. Okay. So, here what you would like to do, your cell center is here. Okay. So, you would like to give less weightage to the value which are very far. Okay. So, the inverse area average is typically a better choice to calculate the value at the nodes, right. So, now you can calculate the value at the nodes and then use this Green-Gauss formulation to get the value at the phase center, and from the phase center you get the value at the get the value of the gradient at the cell center, right. The last missing piece that is remaining is the gradients at the interface, and why do we need that? As we discussed earlier, that if you are going to solve for the viscous problem, so your viscous flux requires the term which requires basically the value of gradient at the phase. Okay. So, this is my phase here. Okay. Good. So, this is my phase. Okay. And we want to get the gradient at this phase. So, for the Euler calculation, you are happy with the value at the phase, which is u k in this case. Okay. But for the viscous flux calculation, you also need grad u k, right. So, how do we get this grad u k? Okay. One thing is that like you use the same Green-Gauss theorem, that Green's theorem that we had discussed earlier. So, when we wanted to get the value at the gradient at the cell, okay. So, this is my I, and we had these phases k equal to 1, 2, 3, 4. So, when we wanted to calculate the gradient at I, so delta phi I was basically sigma phi k n k delta s k divided by your omega I, right. Now, what you can do, you can imagine a co-volume, okay, or it is also called auxiliary volume. So, you have a phase, a cell which is basically connecting to this, okay, and let us call this J, right. So, you can connect all this with the nodes that you have there and create a co-volume, right. Now, for this co-volume, this is your center, okay, and these are your phases, right. These are the 4 phases that you have, right. So, you can use the same approach as we have you had used earlier, that now we want the gradient at k. So, earlier we had wanted gradient at I. So, you considered the actual phases of the cell volume. Now, since we want the value at k, which is the phase center, we would construct a co-volume or auxiliary volume and calculate the value at k, and using the Green's theorem. In that case, your del u k will look like this, okay, del u k or del phi k, whatever you want to say. Okay. So, here this phi k is nothing but the volume of this co-volume, right. So, this is my phi k, okay, this is my co-volume, remember that, okay. And then you have L equal to 1. So, you have now you have to get the values here, L equal to 1, L equal to 2, L equal to 3, L equal to 4, right. So, get the value at the phases of the co-volume, the center of the phases of the co-volume, and then multiply by the normal there, okay, multiply by the area of each of these co-volume phases, okay, and calculate the value, okay. And similarly, here it is very trivial to get the values at different L points, okay. This is L, this is actually L. So, let us say you want to get the value here, this is the co-volume centers, co-volume phase centers. So, you can just take the average of I plus this the vertex phase you have already gotten, right, I plus k1, similarly k1 plus j, j plus k2 and k2 plus I. So, you can do that and you get the value at the center of the co-phases and get the value of gradient at the phase. Okay. So, this is one approach, but a very popular approach is called the diamond path reconstruction. Basically what it does, it can give you the value at the cell gradient which is I here. Okay. So, you want the value delta u I, okay, and you want the value delta u k. Okay. This is needed for reconstruction to get values at phases, and this is for computation of viscous fluxes. Right. So, what we can do that we can make a diamond path. So, this is my actual cell volume, this one is my actual cell volume, okay, and these are my neighbors. Okay. So, this is j equal to 1, j equal to 2, j equal to 3 and j equal to 4, and this is my I, right. So, what you will do that you calculate the first the gradient at the faces like the one we described earlier, right. So, get the values at these vertices, from the vertices take the average, get the values here, okay, and then use the Green's theorem, multiply the value with the normals at each of these co-phase centers, okay, and finally get the gradient at delta u k, right. Once you get the value of delta u k, what you can do is you can take the basically average of these gradients at each of these co-phases to get the gradient at the center of the cell, right. So, once you get this del grad u, what you can do is that you can calculate the grad u I by just considering this gradient at u k multiply with the volume of this sigma k star, which is basically the volume of this the star indicates this is the co-volume, right, and then you multiply with this gradient of that, then you consider this one, you have the gradient here and then multiply with this volume, then you go to the third one, take the the gradient here, multiply with this volume, and finally you have the fourth one, okay, the gradients here, multiply that volume, and finally you can get the gradient at the center of the cell also. So, we got both the gradient in the volume and co-volume, right. So, the co-volume is nothing but the phase gradient, okay, and this is cell gradient, right. So, this is a very popular approach, okay, which is called the diamond path approach, because we are creating a diamond path by connecting the cell centers of the neighboring cells, okay. So, with that we have a fair basically knowledge of how to calculate the gradients in 2D and 3D also. In 1D anyway we discuss a couple of classes back, it is very trivial. Okay. The last thing that I want to discuss is the boundary treatment. Okay. In finite difference it was very easy. Okay. So, what you could do is if it is a finite difference, okay, so you discretize it here, okay, and depending on what value you have, let us say I am solving for del u by del t plus del u by del x equal to 0, okay, and you have the initial condition here, and let us say I am saying using a condition which is let us say u equal to 0 and u equal to 0 here at the boundaries, right. So, you can just assign those values because you have anyway discretize here. So, and you can do away with that. In the cell center approach it is not that easy because you have the value stored at the cell centers. Okay. Your boundary is here, okay, your boundary is here, and the cell center is basically away from the boundary. Here I want to mention one thing that till now what we have discussed is the cell centered finite volume. Okay. There is another one which is the vertex centered, which we have not discussed. finite volume. I think NC-CFX uses this vertex centered, and ANSYS Fluent uses cell centered. Okay. So, in the case of vertex centered, what happens is that for this same problem here, you can basically your vertices becomes the cell center, right. So, it's a bit like your discretization in the finite difference. Okay. So, this is your discretization. So, these are your cells, and the vertex centers are basically the cell centers. Okay. And then you construct the volume around all of this. Okay. So, maybe this is your one cell. Okay. Use another color. This is one cell. Okay. This is another cell. This is another cell. Another cell. Okay. So, these are your cells. Okay. So, here what you get is that at the boundaries you get half cell, right. So, these are your cell centers, okay, and this is your half cell at the boundary, right. So, this is at let us say 0 and this is n, right. So, you get half cell. So, the advantage of this vertex centered approach is that you can basically strongly apply a boundary condition like you do in finite difference, that if your value is 0, you are basically applying at the vertex the value is 0. Okay. In this approach, because your cell where you are storing the values is a little bit away from the wall. So, you will get the value which is you cannot strongly apply the boundary condition, but there are ways to basically ensure that let us say you want to apply no slip or any other kind of boundary condition, digital boundary condition, you can still do that, right. So, this approach is slightly more expensive, okay, and there are certain advantages and disadvantages of the vertex centered compared to the cell centered. For example, in the vertex centered, as I told you, you can strongly apply your boundary conditions, but it is more expensive. The cell centered requires little bit less storage of data, okay, and the computations are also faster, but then applying these kind of digital boundary conditions are not basically very strong. Okay. So, what we do in this approach is we construct something called ghost cell. Okay. So, you want the value of u equal to 0 here, right, and let us say you have some value at this point in this cell. Okay. Here let us say my u is 0.5, okay, and here let us say u is equal to 1 and it goes to equal to 10, let us say, and it goes down here also equal to let us say 0.5, this is equal to 0.5 and this is equal to 1. Okay. Let us consider a kind of symmetric thing. Okay. Now, you have to ensure that at the boundary my value should go to 0. So, again there are many ways to do that. Okay. The one of the approach which is very popular is called the ghost cell approach. So, what we will do, we will construct another cell which is equidistant from here and which is basically outside our boundary domain, and we call that as the ghost cell. Okay. Let us indicate GC. Okay. Similarly, on the right hand side we will put the value which is GC, right. The distance, this one is equal to the distance here. Okay. This one is equal to this one, right. So, what you can do, that you have the the value here u, let us call it u1. So, what you can put the value here u equal to minus u1, minus u1. So, what will happen is that once you take the average or try to calculate the value at the face, your u1 plus minus u1 to cancel out and you will get the value at 0. So, your u value will become 0. Okay. I am using the term average in a loose sense, but you would see that it will be very close to 0, okay, regardless of what flux scheme that you are using. Okay. Similarly, in the right hand side also you can use another value. If let us say if it is temperature and you do not want to put 0. So, let us say I have some value here T1 and here I know the value at the wall T equal to T wall. Okay. So, you will use the value in T ghost cell as let us say Tw minus T1, right, and then you add both the value, you will get the value of Tw at the wall here, right. So, I hope it is clear to you. If it says 2D flow, okay, let us say this is a 2D flow and you have cells everywhere, Okay. So, you basically construct cells which are the ghost cell, okay, across each cell, which looks very similar, okay, and the values of these ghost cells, the cell centers, will be used to compute the value at the face. Okay. So, because the values are stored at the cell center only, right. So, okay, this should be the mirror of that. This should be exactly the mirror of this. Okay. So, if you make a ghost cell, you have little bit more points increasing in the computational domain, which are, let us say if you go from 1 to n plus 1, you will have value 0, and 1 to n it will go 0 to n plus 1. So, you will have at least 2 points if it is 1D increasing because of the ghost cell on the either side. Okay. You can have more number of ghost cells also, maybe you can have 2 ghost cell in this and 2 ghost cell on this side if you have requirement of a higher order scheme, right. So, accordingly you have to consider the bookkeeping that you want to do. Okay. So, what we will do, we will stop here, and in the next class we will look at some of the applications of the finite volume. So, till now we have discussed the theory, okay, how to formulate the finite volume problem, how to calculate the fluxes, and how to reconstruct, okay, how to apply the boundary conditions. Okay. So, all these things we saw. Even if you have a, let us say, Nyman boundary condition instead of Dirichlet boundary condition, you can still make each of the ghost shell there. Okay. So, ghost shell is very useful. If you do not have the ghost shell, you have to somehow ensure that the value that you have the phase is what the value you are getting after the computation. So, some of the codes do not have the implementation of the ghost shell. Okay. So, in next class we will meet, we will start with a simple convection diffusion problem, okay, and then we will go to solve the shock tube problem. Okay. So, that will be last class on the finite volume. I am not discussing many flux scheme. Okay. In the finite volume, you have several different flux schemes, and for example, the most popular is the row scheme. Okay. This is used in even in finite difference sense, and then you have one layer. Okay. Then you have AUSM and AUSM plus. Okay, these are the schemes that you would see in your code in, let us say, in Fluent or OpenFOAM. Okay, these are basically density based solvers. Okay. Okay. Then HLLC. Okay, what they do is that after the reconstruction you got the values at the face, but what you are getting from the left cell and the right cell, let us say this is my face, you reconstructed from left got one value, okay, and you reconstructed from the right got another value, okay, but the flux at the face should be unique, right. So, the flux that you are getting on this face should be unique. So, how do you use this value? This is, let us say, this is phi L and this is phi R, okay, reconstructed value from this to this, okay, at the face, right. So, how do you make use of these two different fluxes to get a unique flux at the face, right. So, that is what there are some requirements there. So that basically one thing is that you can preserve, you can find shocks clearly. Okay. Similarly, you have some kind of projectivity preserving properties that you need to make sure, right. So, all these schemes do that, but what we will do, we will only look at the scheme which we have discussed in the great detail, which is the Lax-Frederick. Okay. This is as we know that this is a very dissipative scheme, but it gives you a decent solution, right. So, this I will urge you to basically go back and look at the literature, and depending on as you start using CFD, okay, and I would not say that go and read about every scheme, but let us say you are using row scheme, please go back and see the details how the row scheme is implemented. There are schemes which are divided into primarily two parts. One is called the flux vector splitting, okay, and other is flux difference splitting. Splitting. Okay. The concept is same, you want to get a unique flux from the left and right constructed values, But how to do that? In this case, you can split the f into f plus and f minus. Here what you do is that you take this f l and f r and you will have some flux difference and multiply by some factor here. Okay. So, as you start using different schemes, go back and read about the theory that how they have been used. In this course, we will not have time to go through each of these schemes, okay, but I will show you one example with Lax-Frederick for the shock tube, which is a very simple scheme, like we use I and I plus 1 in the finite difference. Similarly, we will use left value and right value reconstructed values to calculate the Lax-Frederick flux. Okay. So, these things we will discuss in the next class, and that will be the conclusion of the finite volume, and after that we will go to some more topics like the Raynes aspect, Reynolds or Navier-Stokes, as well as the boundary conditions and then large eddy simulations and so on and so forth. Okay. So, we will stop here and we will see you in the next class. Thank you.